One phenomenon that is unique to the SN1 reactions, and we don't see it with our SN2 reactions, is carbocation rearrangements. So you can imagine why it might be unique for SN1 reactions because we actually do go through a carbocation intermediate in these reactions. And where this comes into play is the following reaction. So if we take a look at treating this compound with sodium iodide and expecting the substitution product, we would see that substitution product that we expect to see where the bromine is substituted for the iodine, we see that product as a minor product. Our major product instead has a structure like this. And so we're going to draw a mechanism and explain this concept, keeping this example in mind because this is the observation. Now we're going to explain why does that happen. And so first steps first, we are going to be able to have that leaving group leave. That's our first step of our SN1 reactions. That's going to give us a carbocation. And what can happen with this carbocation right now, we have a secondary carbocation. And it's secondary because the positively charged carbon is attached to two other carbons, and so we call that the secondary carbocation. What we also see next to the secondary carbocation, and this is what is going to clue us into the fact that we might have a carbocation rearrangement, is a lot of branching on the carbon that is directly attached to the positively charged carbon. So this carbon here is attached to three different CH3 groups. So we do see branching beside this carbocation. And that's signaling to us that we might be able to do a rearrangement. And what this rearrangement involves and why this occurs is when we do have a lot of branching, if we take one of these methyl groups, for example, what can happen is it can essentially just hop over with its electrons. So it basically takes its electrons, picks it up from the carbon it's attached to, and goes and dumps them and shares them with the positively charged carbon and therefore makes a bond to that carbon. And so what that's going to do, and the reason why that type of thing would happen, is that if one of these bonds just left, we would have a positive charge now on this carbon. If that positive charge is on this carbon is attached still to three other carbons, so it would actually make a tertiary carbocation. Let's draw that out. So let's say that we're going to move this one over. The way we show that, we start our arrow in the middle of the bond and then we point to the atom that that bond is going to. So now we're going to have a new bond on the carbon on the left, and there's always an H we're not showing. We can go ahead and draw that in here. It's still here, and it's still here. And so now because that carbon has four bonds, because that new bond from that methyl group hopping over, we don't have a charge. The charge instead is going to be left behind from where that methyl group came from. So if we number our carbons, we could maybe see this a little bit better. So carbon 3 is the one that has all the branching. In our numbering, carbon 4 moved over. 1 and 2 stay the same. 3 is still in the same location, and same with 5 and 6. So what we've done is we've actually made a tertiary carbocation by having one of those methyl groups pick up and move its electrons over to what used to be the carbocation. The reason this happens is that you're going to get a more stable carbocation, and this arrangement could happen before the nucleophile would actually be able to come and attack. Because it's happening within the same molecule, it's going to happen a lot faster. And so we're going to see this rearrangement occurring and giving this carbocation before that iodine has a chance to attack. And that's why we see the major product does have that rearranged skeleton. And if we take the same numbers we were using in our mechanism, we kind of transport them up here, we would see that our carbon 4 would be up there, and then our 5 and 6 will be where the iodine is attached. So then the last step is just to have that iodine come and attack that carbocation. to give our major product in this reaction. And we can draw the H if we want to. We don't really have to keep drawing that in. That's going to give us that major product. And so this happens because it can be sometimes hard to be like, when is this even going to happen? This happens when you have branching beside the positively charged carbon. So we do see numerous bonds to other carbons right beside. This can happen with methyl groups. So something like we just showed. It can also happen with CH bonds, so that instead of being a CH3, number 4, if that was an H, it could do the exact same thing. Our product would look different because we don't show H's on our line structures normally, but it would be the same mechanism. The H would just hop over instead, and then we would end up attacking at kind of a different position than what we expect because of that shift. So both of these types of bonds can kind of migrate over and take their group over. The carbon-carbon bonds we're going to see migrating, we call that a methyl shift. And if it's a CH bond, so the H taking the electrons and migrating over, we call that a hydride shift. And the hydride shift will also occur if we have the other atoms being also carbon groups. So we would still have that potential to form that more substituted carbocation. So that's what we're looking for with our rearrangements, and it is something to be aware of when you're doing SN1 reactions because this can happen.